Hi here, we discussed about the project Enhancing Memory BIST with an optimized RTL-BIST IP core, a low-power, high-fault coverage approach. From this work, embedded memory systems based on static random access memory form the computational backbone of modern digital platforms. These include real-time edge inference engines, autonomous vehicle controllers, aerospace fault-tolerant processors, and industrial Internet of Things devices, where uninterrupted reliability and high data integrity are essential. Although on-chip memory integration significantly enhances system performance, it remains highly susceptible to manufacturing-induced defects. Common fault types include stuck-at faults, transition faults, coupling faults, read-disturb faults, and delay faults. These issues arise primarily due to process variations, voltage scaling, and the aggressive scaling of cell density in advanced CMOS technologies. Conventional March-based memory built-in self-test architectures provide deterministic fault detection. However, they often struggle to detect complex coupling faults while maintaining low hardware overhead and power efficiency within an integrated controller framework. In existing implementations of March SS and March SR, algorithms, while functionally correct, exhibit limited effectiveness in activating and detecting deceptive read-disturb faults and idempotent coupling faults. Additionally, they lack a unified architecture that integrates FIFO buffering and comparator-based verification within a single pipelined data path. To overcome these limitations, this work proposes a FIFO and comparator-based memory built-in self-test architecture using a reference paper, in-field test for permanent faults in FIFO buffers of NOC routers. The design is implemented, simulated, and synthesized using the Xilinx Vivado tool, targeting the Arctic 7 FPGA platform. The proposed system incorporates March SS, March SR, and an enhanced March SR Plus algorithm for comparative analysis. The FIFO-based data path efficiently buffers address and data streams, while the comparator module performs real-time validation of memory responses against expected values. This enables fully pipelined fault detection without introducing additional latency. Overall, the proposed FIFO-based MBIST architecture delivers high fault coverage, improved timing efficiency, and compact hardware utilization. This makes it a strong candidate for safety-critical VLSI applications in artificial intelligence hardware, high-performance computing, and real-time embedded control systems. Now we can verify this work. Here, we designed March SS, March SR, and March SR Plus from the March test algorithm. Here, FIFO buffer is a simple memory structure that stores and transfers data in the exact order it arrives. In other words, the first data written into the memory is the first data that gets read out. In this work, the FIFO is implemented using SRAM cells and is commonly used inside network on-chip routers to temporarily store data packets, also known as flits, before they are forwarded to the next stage. During normal operation, data enters the FIFO through the input line and is stored sequentially using a write pointer. Later, the data is retrieved in the same order using a read pointer, ensuring correct data flow. However, SRAM-based FIFO buffers are vulnerable to faults such as stuck-at faults, transition faults, and read-disturb faults. These faults mainly occur due to aging effects and process variations in modern CMOS technologies. To address this issue, a testing mechanism is integrated into the FIFO architecture. The FIFO operates in two modes, normal mode and test mode. In normal mode, it functions like a standard queue. In test mode, activated by a control signal, the FIFO temporarily halts normal data transfer and uses internally generated test patterns to verify memory correctness. The testing process involves reading the stored data, modifying it, such as inverting the bits, writing it back, and then comparing the results to detect any faults. Importantly, the original data is restored after testing, a method known as transparent testing. This approach enables continuous monitoring of memory health without disturbing the stored data. As a result, the FIFO becomes not only a data storage unit, but also a self-testable and highly reliable component, making it essential for high-performance and safety-critical VLSI systems. The core of this paper's March SR Plus algorithm is designed to overcome the limitations of traditional March-based tests by enhancing fault activation and detection, especially for complex coupling and read-disturb faults. Unlike March SS and March SR, which mainly target basic faults with simpler sequences, SR Plus introduces optimized read-after-read and interleaved operations to improve fault coverage and observability. This enhancement is required because modern high-density SRAMs exhibit complex failure behaviors that conventional algorithms cannot efficiently detect. In this work, we have also integrated March SS and March SR within a FIFO-based MIBST architecture using a comparator to evaluate and validate performance improvements. As a result, SR Plus achieves higher fault coverage and improved reliability with efficient hardware and power utilization. We can verify this simulation process one by one. This is the state diagram of March SS test using FIFO architecture. This flow designed as per the March algorithm's equations, and this is Verilog HDL coding. This is the simulation results of March SS. Here, fault injector will generate the error. Based on that error, the MIBIST react the fault analysis of stuck at, transition, address decode, read disturb, delay detection, and bridging detection. This is the next state diagram of March SR test using FIFO architecture and Verilog HDL coding. This is the simulation results of March SR. And this is the fault analysis results. This is the proposed state diagram of March SR Plus using FIFO architecture and Verilog HDL coding. This is the simulation results of March SR Plus, and this is the fault analysis results. And this is the synthesize analysis of March SR Plus. This is RTL schematic. And next, we have compare this all design and put it on comparison document. Here, all design and test analysis will be compared. And then, we have written an abstract document for this work. Title, Base Paper Abstract, Proposed Title, Proposed Abstract, Introduction, Related Notes, Literature Survey, References. Thank you.
Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join Nxfee Innovation, shaping your future for VLSI research. Are you planning to publish your next innovative research in IEEE transactions on VLSI 2025? Welcome to Nxfee Innovation, where future-ready VLSI research projects are designed with novelty and quality for global researchers. At Nxfee, we provide novelty-based VLSI projects carefully aligned with IEEE transactions on VLSI 2025. These projects are not yet published, offering you a clear opportunity for unique contributions in top-tier journals. Our research covers key domains like low-power VLSI design, analog integrated circuits, FPGA implementation, signal processing architectures, and emerging applications such as cryogenic front-end ASICs, physical unclonable functions, and self-recycling SRAM cells. Each project comes with a verified novelty, simulation results, and complete customization for your journal publication. You'll find practical design files, HDL codes, schematics, and step-by-step explanations to guide your research journey. We provide 100% accurate results and comparisons of source code with all results, basic documentation, and explanation video. We provide execution support with explanation-recorded video explanations on your system. IEEE guidance for paper writing and journal publication. Affordable project packages with ongoing support. Customization to match your research needs. Early bird offers and discounts for researchers. Don't miss the chance to publish in IEEE transactions on VLSI 2025. Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join Nxfee Innovation, shaping your future for VLSI research.